So, hello students. Today we are going to start a new topic called the electromagnetic theory. So, this is a very easy topic. Uh, the whole electromagnetic theory is based only on four laws. Okay. So, what are those laws? Let me write it down. Gauss law in electrostatic. The second one is Gauss law in magnetostatic. The third one is Faraday's law of electromagnetic induction, and the fourth one is Ampere's circuital law. Okay, so the whole electromagnetic theory is based only on these four laws. Okay, and there is one another law which is called the Lorentz force law. Let me also write it down. Okay, Lorentz force law. Okay, so in this chapter we are going to discuss all things, almost all things about these four laws. Okay, and I will just briefly write it down what is the Lorentz force law. So now let me discuss the Gauss law in electrostatic. Okay, so first we write it down. Okay, Gauss law in electrostatics. Okay, so here the first thing I want to ask you is what is flux? We all know about flux, right? So what is flux? Flux is what? Flux is field lines or line of lines of force per unit area. Okay, I want to add one word here. Passing line of force passing normally. Okay, so flux means field lines per unit area, and it is the field lines must pass through it normally. Okay, so what is it? So if this is an surface, okay, uh, let's say its normal direction is in this way towards right. Okay, let me denote it by n cap. And if there are, let's say, electric field lines, okay, if this is these are the electric field lines, okay, and this is these are making an angle theta with n cap. Let me write it down as capital E factor. Okay, so if this is the angle theta, then we we know that we have to take the what cos theta component, because the electric field lines which we will consider for flux must pass through the surface area what normally. Okay, so the field lines must pass through it normally. And then if I can denote it by phi, the flux, if I denote it by phi, then what will be its value? Okay, so phi will be equal to integration of what E dot ds. So why there is dot product? This dot product is just because of this cos theta component. Okay, so this is coming because of the normal component. So let me denote it. Okay, so if phi is what? Phi is flux, that means field lines per unit area. And what is E? E is lines of force per unit area. Lines of force what? Per unit area. Okay. Okay. And this is what? This is dot product. Dot product. This is because of the normal component. Because we need to consider the normal component only. Component only. Okay. So now let me proceed further. Okay. Okay. So now what is Gauss law? Okay. So now if this was an open surface, right? So if I consider a closed surface, let's say this is an spherical surface. Okay, so this surface is what? This surface is enclosing. Okay, enclosing and volume. So this is a closed surface. So let denote it by S. And this is, if this is the total amount of charge, let's say Q, which is enclosed by the surface, then what will be the flux? So this is given by Gauss law. Okay, so phi will be the flux, which will be equal to Q, let's say ENC. ENC means enclosed. Okay, Q ENC equals to enclosed charge by the surface. Okay, and divided by what? Epsilon. So in case of free space, this will be epsilon naught. In case of free space or vacuum, okay, epsilon will be converted to epsilon dot. Then flux will be what? Q enclosed divided by epsilon. So what? This is the Gauss law. Okay, and what we can write? As we have seen, phi equals to E dot ds. Okay, so if the surface is closed surface, okay, so if the surface is closed surface, what I can write? Phi equals to close integration what? E dot ds, right? Because the surface is enclosing some volume, that's why I am writing it down as what? As closed integration. Okay. So what will be its value? This will be what? QENC by epsilon. So this is the integral form of Gauss law. Okay. So this is the integral form of Gauss law. Integral form of Gauss law. Okay. So now I want to discuss about the differential form. So this we have learned in one, this we have learned in higher secondary also. So now what I want to discuss with you is the differential form. Okay, differential form. So what is the differential form? So for differential form we will use the Gauss divergence formula. Okay, so first let me write it down. The integral form is like this, right? U enclosed by epsilon. Now let me discuss with you just one thing. Okay, first let me add some space here. Okay, okay, so let's say this is a what, this is an sphere. Okay, so if this sphere is enclosing a volume V, okay, and the its charge density is rho, then what I can write, that I can write that q enclosed, that means the total charge inside this volume will be what, rho into V, right? And what I can write down as V, the V can be written as what, integration of what, dV, right? एक छोटा सा वॉल्यूम ले लिया, I have taken an, we have taken an small volume dV, and then we multiply it by rho and then integrate over the whole volume, then we will get what, we will get the total charge, right? Where rho is the what, rho is the charge density, is equals to charge density. Okay, rho is charge density. So what I can write here, q enclosed can be written as integration rho by epsilon naught dv, right? And now what I can write from Gauss divergence formula, what I can write, okay, let me write it down. From Gauss divergence formula, the closed integration of E dot ds can be written as integration divergence of the field vector into dv. So this is coming from Gauss divergence formula. From Gauss divergence formula, for any vector, let's say for any vector capital A, for a closed surface, the surface integration can be written as the divergence of the vector A and its volume integral. I hope you understand this. Okay, okay, so this is what, this is from Gauss divergence formula. So if I want to, okay, let me write it down here, E dot ds, okay, this is dot product 1, and if this is 2, so putting 2 in 1, okay, let me insert some space. So what, putting 2 in 1, we can write what we can write, we can write that, okay, the volume, so this will be the left side, okay, the divergence of the electric field and its volume integration will be equal to what, will be equal to integration of rho by epsilon naught dv. Okay, so moving this towards left, what we can get, we can get del dot E dv minus, okay, minus rho by epsilon naught dv equals to 0. Okay, this is integration. So now what we can do, by combining these two, del dot E minus rho by epsilon naught dv is equals to 0. As you can see, the value of the integration is independent of the volume, total volume, okay, so it doesn't matter what is the volume dv, okay, so if the surface is enclosing this much of volume, okay, let's say this is p1 and let's say this is what, this is p2, Okay. Yes. Okay. So this is V1. Let's say this is V2. The total volume V2. It doesn't matter whether the surface is enclosing this much of volume V1, the smaller one, or the bigger one. It doesn't matter. Okay. So the total, the integration value is zero, independent of the amount of volume enclosed by the surface. So which means, okay, let me write it down. Since the since the uh, okay, since the value of the integration is zero, independent of the amount of volume enclosed by the surface. So the integral must be equals to zero. Okay, the integral must be equals to zero. So what we can write? So we can write from here del dot E equals to rho by epsilon naught. Okay. So this is what? This is the Gauss law in electrostatic. Gauss law in electrostatic. This is what? This is differential form. Okay. Differential form. Now I want to discuss the second law. Okay. Gauss law in magnetostatic. Okay. So first of all, I want to discuss that the magnetic monopole doesn't exist. Okay. So if this is okay, if this is a bar magnet, let's say this is N, this is S. Okay. So the field lines are coming from north to south. Okay. Like this way, right? Okay. So the number of field lines coming out of the north pole is equal to the number of field lines entering the south pole, right? Okay. So now if we what if we break the bar magnet in two halves. Okay, let's say break it here. Okay, then what will happen? Then now this will be two halves. Okay, so this will be N, this will be S, this will be N, this will be S. Okay, so these two will act as two different bar magnets. Okay, so let's say let me break it here. Okay, so now for this part, what will happen? This north pole will remain as north pole, and this south pole there will be another south pole. Okay, and for this part this will be remain as south pole, and here there will be another north pole. So now the field lines will look like this. Okay, so if we consider a closed surface anywhere. Okay, okay, let's say if we con if we consider the surface like this, then what will happen? Then there is no surface coming out of the surface. There is no field lines which are coming uh, out of the surface and which are going inside the surface, right? There are no field lines. So the total flux, what? The total flux will be equals to zero. And if you consider like a surface like here, then for this surface also, what will happen? The total number of field lines or flux will be what? 0 coming out of the surface will be, and the number of field lengths coming inside the surface will be number of field lengths going outside the surface, right? Because you can, as you can see, uh, if we break the bar magnet at this part, at this position, then what will happen? We can always consider a surface like this. For this part, what we can write, we can write this as, okay. So now if I consider a closed surface, okay, so if this is a closed surface, okay, so and inside there is a bar magnet or anything, okay, so it doesn't matter, the magnet should be inside the whole surface. Let's say this is like that, okay, let's say this is north pole, this is south pole. Then for this case also, for any other case, the number of field lines going inside the surface will be what, the number of field lines coming out of the surface, right? So we all know that the total for an enclosed surface, what b dot ds equals to 0, right? Because this is just because of magnetic monopole doesn't exist, okay. So what I can write, b dot ds equals to 0, because number of field lengths going outside the surface is number of field lengths coming inside the surface, right? Okay, so now similarly, from what, from again from Gauss divergence formula, what I can write, I can write it down as, okay, let me add some space here, okay. So okay, let me shift it from here to here. Okay, so now what I can write, from Gauss divergence formula, from Gauss divergence formula, what I can write b dot ds equals to divergence of factor b in the volume integration of dv. Okay, so if we put this here, what we will get? Okay, this is, let's say, okay, 3, and this is, let's say, what, 4. Okay, so putting 4 in 3, we get what? We get dv equals to 0. Again, the same thing, the integration value is 0 independent of the volume enclosed. So what I can write? I can write divergence of b is 0. So this is what? This is the Gauss law in magnetostatics. And this is what? This is the differential form. Differential form of Gauss law in magnetostatic. Okay, so this is the differential form of Gauss law in magnetostatics. So now proceeding forward, now what I want to discuss, now I want to discuss about the third law, okay, Faraday's law of EM induction. Faraday's law of EM induction. So now what do you know? If this is a closed loop, okay, this is an closed loop. Let's say this loop is perpendicular to the what? Perpendicular to our let's say computer screen or mobile screen. Okay, so if this is like that, and okay, let me write it, this is right side, this is left side. Okay, and it's what it's like direction factor is in this direction. Okay, let's say n cap. If now there is a bar magnet which is here north and south, then if we want to push this bar magnet towards the loop, then what will happen? And then in the right side of the loop there will be north polarity developed. Okay, and what will happen, this north polarity will try to push away the magnet, but since we have to do some work while moving this bar magnet towards the loop, right? And if we try to move this away from the loop, this is n side, then what, then for this loop what will happen, there will be a south polarity developed. Okay, and this will what, this will produce some attraction force between this loop and the bar magnet. So if we have to move this bar magnet away from the loop, then we have to do some work, because this north and this south pole will be what attracts each other. Then similarly for south pole there will be opposite. Okay, so I hope you know that. And this is the direction of current flow. Okay, so when there is a relative motion between this loop and the bar magnet, the what will happen? There will be a current flow in the closed loop. That means there will be an EMF generated. Okay, so let me write it down as relative motion between the loop and the magnet. Let's say bar magnet. Okay, bar magnet will cause will cause change in flux in the loop or through the loop. Okay, flux through the loop. So there will be an EMF generated. Okay, so since current is flowing in this circuit, so we can say that there is an EMF generated, right? What EMF stands for? Okay, EMF stands for electromotive force. Electromotive okay. Electromotive force. Okay, so the what is the amount of this EMF which is generated? So this generated EMF can be written as minus d phi dt. So the rate of change of flux will be equal to the what EMF generated, and in terms of uh, field lines we can write down it as E dot dl. So this is the EMF generated. Okay, so now using Stokes law, okay, this is the closed loop. Okay, so using Stokes law, what I can write from Stokes law, I can write down that E dot dlb will be equals to what, the cross product of E with del, that means curl of E and its surface integration. E ds. Okay, so now what we can write again, for this is magnetic flux, right? Because the bar from the bar magnet in the loop there will be what magnetic flux, right? Okay, so if there is a relative motion between this bar magnet and loop, the amount of flux in through the loop will be changed, right? Okay, so for phi b, what I can write from Gauss law in magnetostatics, what I can write it down as division of b dot ds, right? So what I can write, if we replace this and this here, okay, so what I can write, okay, let's mark it what, let's say this is 5, this is 6, putting 5 and 6 in above equation, what we will get, we will get, okay, I am making a mistake here. This will be normal integration. So integration, okay, del cross E ds will be equals to integration b dot ds, ये minus होगा, there will be n minus del t minus d dt of integration of b dot ds, right? So now if I want to take this differentiation inside, what I can write, del b del t, right? ds. Now let's move this towards left, then what we will get, del cross E, okay, let me add some space here, okay, so what will I can write, del cross E ds plus integration del b del t ds, this will be equals to 0. Now what I can write, I can write this as, by combining these two terms, okay, sorry, okay, plus del b del t dot ds will be equals to 0. Now similarly, as we have talked before, this value of integration is 0 independent of the surface, right? So what I can write, I can write it down as equals to minus, okay, let me add a line here, okay, plus del b del t equals to 0. But now let move the second term towards right, then what I can write, I can write del b del t. So this is the Faraday's law of electromagnetic induction, okay, okay, so this is the Faraday's law of EM induction, electromagnetic induction, okay. So all these four laws, okay, let me clarify one thing here, okay, तो मैं यहाँ पर एक square box बना रहा हूँ, I am making this square box and I am clarifying some things, okay. So whenever I am writing, let's say here is some term, okay, let's say something, let's say b or c, some and then ds. This is not a single integration, okay, this is an actually double integration because this is an surface integration, okay. And whenever I am writing this as dv integration, there are three line integrations, okay, but we can simply write it down as single integration. It's not a big deal because since it is written as dv, so you can write it down like a single integration. Teacher will understand that, so don't worry about, okay. So now moving forward, now I want to discuss the ampere circuital law, okay. Okay, now ampere's circuital law, okay. So what we have learned in higher secondary, okay, what we have learned in higher secondary is that if there is, let's say this is a current carrying conductor, let's say the amount of current flowing in this conductor is I, then using right hand thumb rule, what we can say, we can say okay, okay, right, using right hand thumb rule, what we can say, the magnetic fields across around this current carrying conductor will be what, this will be look like this, okay. Okay, so using right hand thumb rule, what we can, let's say this is the magnetic field, okay, this will be a circular flow, okay. So now from ampere circuital law, what we have learned, if we take a line integration, okay, let's say this is then, this is an element, let's say length element dl, then what we can write, we can write that b dot dl equals to what, mu naught I, okay. And this is what, this is an closed integration, right. So here, um, here what, this is the ampere circuital law, okay. Okay, so first let me tell you one thing, that all these four laws I am discussing with you is known as Maxwell equation, and these were given by what, Maxwell, okay. So this equation, okay, so there is an actually some problem here, right, okay. This equation max according to, so Maxwell what find out that if there, this is a resistive circuit, okay. So if let's say there is a no capacitor like resistance or what, like let's say this is resistance, okay, let me properly write it down, okay. If this is an resistance, let's say this is an battery, so in this circuit, oh okay, the circuit is what, closed, okay. So we can always write it down as I, let's say this is an conduction current I. So there, now let's say if there is a capacitor in this circuit, let's say this is an battery and this is a capacitor. So while the capacitor is being charged, let's say the current is moving from this side to this side, right. So well, when the capacitor is being charged, then what will happen, due to the change in electric field, right, here the positive charge will be deposited and there will be a electric field from this to this. So when the electric field, as the charge is being deposited, the what will happen, the electric field will be keep changing, right. So there will be an current till the capacitor is fully charged, right. Till the electric field is changing, there will be a current, okay, current in this direction, right. If we consider a closed loop here, let's say in this position, so there is actually no current flow, okay, right. So since there is no conduction current, right, so current, to flow the current, there must be some conductor, right, okay. So Okay. Mm. So to actually flow the current, there must some have conductor so that the current can flow through it, right? So but in this position, the between the plates of the capacitor, there is no actually what conductor, right? So but still there is a current flowing when the electric field is changing, right? So when the electric field is changing, so Maxwell given a correction term that there is a current, right? So when the electric field between these plates are changing, then there will be a current called displacement current, id. Okay. So this is a displacement current, id, displacement current. So what is the difference between conduction current? Let's say write it down as IC and ID. So what is the difference between conduction current and displacement current? So for conduction current, there is a conductor, right? And the current is actually flowing through it. But the concept of displacement current is that for a changing electric field, changing, remember the word changing. If the electric field is static, then there will be no displacement current. Okay. So while the electric field is changing between the plates of the capacitor, there will be a current, so that the ampere circuitry law is what valid. So this current is called what? Displacement current. Okay. So what he has written, according to Maxwell, he wrote it down as B dot ds equals to mu naught IC plus ID. So here when this is there is a conductor and here is a current is flowing, in this case IC is there and there is no what? ID. So for conductor, displacement current नहीं होगा. So in this case there is no displacement current since there is an actual current, that means conduction current. And while in this case, while for the case of changing electric field, there will be an displacement current, not conduction current. So that so what I can write it down as B dot dl will be equals to what? Okay, will be mu naught IC plus ID, where the total current is the sum of IC plus ID. Okay. So now for conduction current, what I can write for conduction current, I can write it as J current surface current density dot ds. Okay. And for displacement current, what I can write it down? This is simple equation. I think you have understood. If this is an surface, let's say this has surface area what? Let's say S. Then if the current density is J, then the total current will be what? Total J dot S. So if we take a small area, let's say ds, then what we can write? This will be equals to J dot ds. I think this is simple, very much simple. And then for displacement current, what we can write? For displacement current, there will be a term epsilon del E del T ds. Okay. So now from where this term is coming, I will explain it just after writing down the whole equation. Okay. So first let me write it down. Okay. So now what I can write from Ampere's circular law, what we are getting that mu naught IC plus okay, let me write it down separately. Mu naught I plus mu naught, this is conduction current and this is mu naught ID. Okay, so using again Stokes law, what I can write? Del cross B dot ds will be equals to mu naught, just replace it here. Okay, So what we'll get, IC will be equals to integration j dot ds plus mu naught, while what will be ID, epsilon del E del T dot ds, right? So now what we can write? Okay, so obviously similar thing, we'll move these terms here, okay, towards the left side, and then combine. I am writing down the two steps together. Okay, so what I can write, del cross B minus mu naught J minus epsilon naught mu naught del E del T ds equals to 0. Okay, so now what will happen, I can write down as del cross B minus mu naught J, same thing. Okay, same argument, all these are same argument. Integration value is 0 independent of the surface enclosed by the line. So what, enclosed by the loop, so what I can write, mu naught epsilon naught del E del T equals to 0. So del cross B equals to mu naught, okay, this is a factor term. Okay, mu naught J plus mu naught epsilon naught del E del T, right? So this is what, this is corrected Ampere's law. Okay, or you can say modified. Yes, law. Because what why I am saying modified, because the initial Ampere's law is, this is not also even wrong, because why, because this is obviously true for what, true for resistive circuit. This is true for resistive circuit. If there is no capacitor, if there is no capacitor, then what I can write this as this. Okay, but now since there is the capacitor, so we have to modify something. So this is the ID term, uh, displacement current term. Now I want to talk from where this ID value is coming. Okay, so for this, what I have to tell you, I have to tell you what is equation of continuity. I hope you all know equation of continuity, right? Equation of continuity. So from equation of continuity, what we know, del dot j plus del rho del t equals to 0, right? So now I want to talk you from where id equals to this term is coming, right? Id equals to, okay, integration mu naught, okay, mu naught is not there, f's, and again I am writing this epsilon naught del E del T ds. Okay, so epsilon naught del E del T dot ds. Okay, so as we know from equation of continuity, this term is, right, this term is what, this term is 0. Okay, this is the equation of continuity, this term is 0. Now when I am writing, okay, from Ampere's law, what I was writing, B dot dl equals to mu naught I conduction current. Okay, the initial Ampere circuital equation was this. Okay, so when I am going to okay, I see. Okay, so when I am going to replace these by, okay, using Stokes law, then what I will get? Del cross B ds, right, will be equals to what? Mu naught, and IC can be written as J dot ds. I have already proved you this. Okay, this was okay. Sorry. Okay. Okay. So from here, this is coming. Okay. So now again the same argument. Okay. Okay. Let's do the same thing. Del cross B minus mu naught J ds will be equals to 0, and then del cross B will be equals to mu naught Z. The same argument I am using. Okay, since the integration value is 0, the integration must have to be 0. Now if I want to take the divergence, okay, taking divergence, okay, what I will get? Okay, okay, taking divergence, I will get del cross B will be equals to mu naught del dot Z. How I am writing this, I hope you get it. So first of all, this will be like this. Okay, this is me. Okay, mm, mu naught J, right? Mu naught J, but since mu naught is constant, I am writing outside the divergence term and I am writing it down as this. Okay, so now as we can see, we know that divergence of curl of this any factor is obviously this will be equals to what? This will be equals to 0, but now this term is not 0 because we know that from equation of continuity what we get? We get del dot j plus del rho del t is 0, but this term is not 0, right? Since this is 0, this can't be 0. Okay, so I have to make some correction. Okay, so we are making some correction here. So what we can write? Okay, making correction, what we get? We get del dot del cross b equals to mu naught del of j, okay, sorry, plus del rho del t. Now this term is from equation of continuity. This term is what? This term is 0, right? And again this is also 0, right? So now what I can write? Now I can write it as mu naught del of j. Now what is rho? Okay, so okay, let me change here one thing. So first let me write that down. What is rho? Now we are going to make change in rho. Rho can be written as what? So we all know that what del of E. Okay, let me remove it. We know del of E equals to rho by epsilon. This is what? This is a Gauss law in electrostatics. So right, so what I can write? Rho is equals to epsilon del of E, right? So now replace it here using this in, okay, above equation. What we will get? The left term will be same, del cross b equals to what? Mu naught del of j, divergence of j, plus del rho del t can be del t of what? Okay, let me use hard bracket here. Okay, and then epsilon, rho is, I am replacing rho with this. Okay, so epsilon naught, okay, this is epsilon naught. Okay, so now, okay, there was a term mu naught. Okay, so okay, mu naught, and then del of j plus what? Epsilon will be outside. Okay, and then I can also del of del e del t, right? So now what I can write? Since this term are constant, it doesn't matter whether I write them inside the divergence term or outside them. So what I can write? Del of what? Mu naught j plus, okay, mu naught epsilon naught. This mu I am will be also multiplied with this term. So mu naught epsilon naught del e del t. Okay, so if we remove both the divergence term, okay, so divergence sum from here also, what we will get? Del cross b equals to mu naught j plus mu naught epsilon naught del e del t. So this was the corrected Maxwell equation. And from this term, if we compare, okay, so if from this term, if we compare with, okay, what b dot dl equals to what? Mu naught ic plus id, what we will get? So from here, id will be what? Okay, this can be written as del cross b integration of ds, right? So what I can write? Okay, mu naught j, okay, integration of what? Let's say, okay, del cross b integration j dot ds, okay, plus, okay, mu naught, I can write mu naught outside, right? Let me write it down outside. So mu naught I am writing outside, mu naught integration z dot ds plus epsilon naught del e del t, okay, dot ds. So I can write it down like this. Okay, so what is id? By comparing with this, I can write down id as, so id equals to what? Mu naught, okay, there will be no mu naught term, mu naught term is outside, so id will be this term, right? So id will be what? Epsilon naught del e del t ds, right? So this is the id term. Okay, let me write it down again, that's not clear. Dot ds, right? So from here we got id term, right? So we can write down id as this. So this is the what maxwell's corrected ampere's corrected ampere circuital law. Okay. So till now what we have got, we have got all the four maxwell equation. So these four equations are known as maxwell equation. So I am writing it down. Hashtag maxwell's equations. Okay. So what was the first equation? The first equation was del of E equals to rho by epsilon naught. What was the second one? Del of B, divergence of B is equals to 0. What was the third one? The third one was del cross E equals to minus del B del T. And what was the fourth one? The fourth one was del cross B equals to mu naught J plus epsilon naught, mu naught epsilon naught del E del T. So all these four are known as Maxwell equations. So beside these, I already have told you that Lorentz force law, right? So what is the Lorentz force law? Lorentz force law. I am not going to write it down. I am not going to discuss about this in a broad manner. I am just going to write it down, okay? Because we all know what is Lorentz force law, right? So the Lorentz force law, if a charge is moving, charge q is moving in a magnetic field, then what I can in a electric field and magnetic field, okay? If some space have both electric and magnetic field, then the force on the charge q can be written as q epsilon plus v cross b. So this is the Lorentz force law. I am not going to discuss about it in very much because this is a simple higher secondary type question. Okay. Okay. So this is I think this is the end of today's class. In tomorrow's class, from this equation, how we can find the equation of an wave, okay, and then the properties of those electromagnetic wave I will discuss. So let's end here today, okay? So thank you.